Maximum twin sum of linked list. In a linked list of size n, where n is even, the ith node, 0 indexed, of the linked list is known as the twin of n minus 1 minus I, the node. Okay. If I is between 0 and n over 2, minus 1, so like for example, here if n is equal to 4, then node 0 is the twin of node 3. So this is just basically how this works is we're going to look at all of the indexes that appear before the halfway point of the list, and to find their twin you pretty much just run it through this algorithm. So you take the length, which is n, so when n is equal to 4, you do 4 minus 1, that's just constant, minus I, so the twin of 0, so we want to do minus 0, then that's going to be 3, right? So as you can see, if we want to find the twin of 0, it's 3 in the list of length 4. So then we have a list of length 4 and then nodes 1, so it's 4 minus 1 minus 1, because we want to find the twin of 1 now. That would be 2. So basically, and we want to find the greatest twin sum, and the twin sum is pretty much just the sum of both twin nodes. Okay, and we want to find the maximum twin sum. So basically, if you like actually look at the list, twin is pretty much just like the opposite ends of the nodes. So that's where like the first pair would be, and then you go in one on both ends, and both of those would be like a pair. You can think about like a 2-pointer algorithm where both pointers start at the very outside and then go iterate inwards once every time, and each of those times it would be like a twin pair. So a good way to do this is, first you want to use a 2-pointer technique to find the halfway point of this node, right? Or the halfway point of this linked list. So you can have a fast pointer which goes to the very end of the linked list, and then a slow pointer that's going to go at half the speed, so it would naturally end up at the middle. Then you would insert a previous node, which would be equal to none, and then you'd pretty much just run a reversal algorithm from the middle to the end using that slow node and then the previous node. Now you would have reversed the second half of the linked list. So now what you can do is you can pretty much just, so at this point previous would be at the very last node in this linked list. The reason for that would be because slow, so pretty much when you're doing the reversal algorithm, you're going to have slow go until it's one past the end of the linked list, so previous would end at the end, and then the head would still be at the beginning, right? So now we have a pointer at the very end of the linked list and then a pointer at the very beginning. And so now what you can do is we can iteratively add add whatever the value is at head and whatever the value is at previous, and then move them forward one every time. That was the entire reason why we did the reversal part, was because then we have like, you know, a head at the beginning of one of the linked lists going in one direction, and we want like, because if you look at this, right, we can't actually use like the algorithm that we want going inwards and iteratively like adding both the twin sums, or getting the twin sum every time, right? Because it just goes in one direction. That's why we reverse the right side of the linked list, because we reverse it, then we can make that go inwards, and then the left side will already go inwards, and then and then we can pretty much just add the values at every iteration and find the greatest maximum twin sum. Okay, so let's cover this up. So first thing you want to do is you want to reverse the second half of the linked list. Okay. Now I'm tired. Okay, you want to reverse second half linked list, but to do that, it's not the first thing you want to do. Actually, first thing you want to do is find the middle of the linked list. So we're going to do fast is equal to head, slow is equal to head, while head and the head dot next. Oh, sorry, well, fast and fast dot next. So it's fast and fast dot next because this will confirm that fast finishes at the end of the list, and slow ends up at the middle. Slow, fast dot next. Okay, so now we're gonna previous equal. So this is the first part, right? Finding the middle of the list. Find the middle of the linked list. That's gonna be slow. And then the second part here is reverse the, after we find the middle of the actual linked list, now we want to reverse the second half of the linked list. So what we're gonna do is we're pretty much just gonna do while slow, next node is going to be equal to slow dot next. Slow dot next is going to be equal to previous, and previous and slow. Previous is going to be what slow is at, and slow is going to be where next node is at. And then what we want to do after that, after we reverse the second half of the linked list, what we want to do is we want to bring them inwards, right? Towards the middle now, and add every time, at every iteration. So yeah, okay, so basically just find, so now we want to actually find greatest twin sum. So basically greatest can start off by being 0, and then while previous, pretty much. So while previous going inwards, what we're going to do is sum is equal to previous dot val plus head dot val, and we're going to do if sum is greater than greatest, then greatest is equal to sum, and then previous equal previous dot next, head is equal to head dot next, and greatest. Okay, so the time complexity of this is O of n, because in the worst case we're pretty much just iterating through the entire list, because after we iterate through the entire list, after we iterate through the entire list, which would, because pretty much to find the middle, right, we're going to the end once, and then we're going through half the list again to reverse the second half, and then we're going back inwards. We're going back inwards to find the greatest twin sum. But all these really you just call them O of n. So maybe O of n divided by 2, O of n divided by 2. Alright, O of n. It's all just O of n. The extra space, we're not creating an extra space. We're just doing it with the linked list that we were given. So it's O of 1. And that's the solution here.